Hello Stings. In this video we are looking at graphing quadratics and their transformations. We have our notes page here, which is going to be a foldable. This will be the back side. We're going to fold this in half. On the front we will be sketching graphs of quadratics. Let me bring this up now. Okay. So in order to sketch these graphs, we're going to go ahead and look at the axis of symmetry. B is -4 and A is 1. So in our formula we have -b over 2a. A is 1, B is -4. To simplify this, we end up with 4 over 2, which is 2. So that tells me that the x value of my vertex is 2. So I would like to put a 2 in the middle here, so that when I sketch, I will have a nice symmetric graph. So here we have x squared, so let's go to the calculator in y equals and put in x squared minus 4x plus 3 and look at the table of values. We are specifically looking at values of x from 0 to 4 and what their y value is, so we get 3, 0, -1, 0, and 3. As we can see, here's the vertex, and then the y's are repeating on either side of that. Now we just need to graph these few points. 0, 3, 1, 2, 3, 1, 0, 2, -1, 3, 0, and 4, 3. So here we have our sketch. We have our vertex at 2, -1, and they want to know the solutions. Remember that solutions are also called zeros. They are also called x-intercepts. X-intercepts, zeros, and solutions are all where the y values are 0, so we can even just look at the table here. When y is 0, x is 1. That's this point here. So we have x equals 1 as a solution, and the second solution here, because this crosses the x-axis twice, y is 0 when x is 3, so x equals 3 is a solution to y equals x squared minus 4x plus 3. Looking at the next example, we have y equals x squared minus 2x minus 3. Make that a little bit bigger. So here we have x equals, and our b is a -2, so we want b over 2 times a, which in this case is 1. This will simplify to be x equals 1. So we know that we want 1 in the middle. We're going to go 2 up and 2 down. So then we go to y equals in the calculator to help us get our table, and we will put x squared minus 2x minus 3 and look at that table of values, specifically -1 to 3. So we get 0, -3, -4, -3, and 0. Again, we can see that here's our vertex and that the y's repeat on either side of that vertex. So we can go ahead and graph these points: -1, 0, 0, -3, 1, -4, 2, -3, and 3, 0. So we go ahead and sketch this graph. And we see that we again have two solutions. We have two x values that give us 0 for y. So we have x equals -1, which is right here. And here's the x equals 3, which is the second solution. So this one also had two solutions because it crossed the x-axis twice. In our next example, we have y equals x squared minus 5x. And in this case, b is -5 and a is 1. So we have x equals -b, and b in this case is -5 over 2 times 1. So this will simplify to be 5 halves. 5 halves is 2.5. So we're going to go ahead and put 2, 3, 4, 1. Just do 0 to 4, 2.5 being halfway between 2 and 3. We can type in x squared minus 5x plus 6 and look at the table of values, specifically from 0 to 4, and we get 6, 2, 0, 0, and 2. We do not see the value for the vertex here, but we can see that things are starting to repeat. And if you go look back in the table, 5 is also 6, and then we can see that somewhere in between here is where it has its lowest value, and then it's moving up from there. So we can go ahead and graph these. 0, 1, 2, 3, 4, 5, 6 is the first point. Second point is over 1 up 2. The second point is 2, 0. We're not going to have the vertex, but we are going to go over to 3, 0, and then over 4 and up 2. And we see the symmetry here. I'm going to go down just a little bit. Since this is a sketch, we don't have to be exact, but we do see that x equals 2 and x equals 3 are our solutions. So sometimes the axis of symmetry is not a nice pretty whole number, so we have to look at what's happening around that and know that we're going to either come a little further down or we're going to go up depending on whether A is positive or negative. So here in the final example for sketching the graphs, we have x squared minus x minus 2. In this case, b is negative 1 and a is positive 1. So x equals negative b over 2a. A is 1, but b is negative 1. So that gives us a positive 1/2. Again, we're not going to see 1/2 here, but we are going to have a 0, a 1, and we'll just do 2, 3, and go ahead on the other side of 0 and do negative 1. So when we place this into y equals, we are going to get x squared minus x minus 2, and look at its table, and we're going to start here where x is negative 1, and just copy that information down. You get 0, negative 2, negative 2, 0, and 4. Then we can plot these points, negative 1, 0, 0, negative 2, 1, negative 2. And so we know that this is going to go down below negative 2. So we have 2, 0 as another point, and 4, 3 as another point. So we have this part going up here, but this is going to dip below those two a little bit. Not quite sure how much, but we do know that it's going to go below them because that's our vertex, and it's going to be below these two. So our solutions are negative 1 and positive 2, because these are where the graph crosses the x-axis. It is where the value of y is 0. So these are our solutions. So that is very quickly a brief review of sketching quadratics using the axis of symmetry to help you determine your table values so that you can get things on either side of that and get something a little more symmetrical that looks like a parabola. So now we will be discussing transformations. We have several kinds of transformations. When we have the function being ax squared plus c, which means b equals 0 in this case, we have several things going on. We look at the sign of a. The sign tells us whether there is a reflection or not. If it's negative, there is a reflection. The a tells us whether we have what is called a stretch or a compression. And then finally, c tells us if we have a translation. And that translation is either up or down, depending on the value of c. If it's positive, the graph goes up. If it's negative, the graph goes down. A stretch will take and hold the graph at its vertex and take these and stretch them up, meaning that the two sides come closer to the y-axis. A compression is like you are pressing down on it, and it's going to widen it out. So let's look at the parent function. if we let x be -2, -1, 0, 1, and 2, then this is the graph that we are going to get. The parent function is already graphed for us, so now we just have to look at these, well, no we don't. We need to find the y values here. -2 squared is 4, -1 squared is 1, 0 is 0, 1 is 1, and 2 gives us 4. So this is a part of the data set to get our points to graph the parent function. And this will remain the same throughout all of the examples. G of x equals x squared plus 2. Again, we are going to use the same numbers for x and then plug those in. If you would like, you can go to y equals and you can put x squared plus 2 there and look at a table of values. We will be looking from -2 to +2. So we can just copy those down. We get 6, 3, 2, 3, and 6. So these will be the points that we are going to plot to see what g of x looks like. So we go to -2 and we go up 6. We go to -1 and we go up 3. 1, 2, 3. We go to 0 and it goes up to 2. 1 goes up to 3. And then 2 again goes up to 6. So what has happened here is, if I can draw this a little bit better, all we've taken is we've taken the parent function and moved that whole thing up 2 units. So what happened to the parabola for g of x? It was translated, and by it I mean the parent function, was translated up 2 units. So when we look at h of x, we are looking this time at x squared minus 2. So again, we'll use -2, -1, 0, 1, and 2. And when we look at the table of values for x squared minus 2, we get 2, -1, -2, -1, and +2. So for h of x, when we go to -2, we get a +2. When we go to -1, we get a -1. When we go to 0, we get a -2 for our y. 1 gives us a -1, and +2 gives us a +2. So this time, we have taken the parent function and moved it down 2 units. So h of x is the parent function translated down 2 units. Okay. So this is basically a change to c, because what we did here was a was 1 for the parent function, and in both g of x, a was again 1. But this time, instead of in the parent function with c equaling 0, we had c being +2 or -2. So let's look at what happens when we make a change to a. So these examples are based off, again, of the parent function. So we'll go ahead and copy down this table of values. We just found it in the previous example. And here's our parent function. And this time we see that with g of x, what we've done is changed the 1 to a 2. So we're going to look at the same values of x so that we can see what's happening. So we have 2 times the letter x, or the variable x, squared. So x is what's being squared, and we're just doubling that. So let's look at the table of values. So this time, -2 is a +8, -1 yields 2, 0 yields 0, 1 yields 2, and 2 yields 8. So we can see 0, 0 again. They share the vertex, and then we just need to graph these ordered pairs. So negative 2 goes all the way up to 8. Negative 1 goes up to 2. They share a vertex. 1 goes up to 2, and 2 goes up to 8. So we can see that the values of the parent function here, like negative 2 with the parent function was 4, but now that's been stretched up to be 8. This negative 1 gave a positive 1 in the parent function, but it's double that to positive 2 in g of x. Same thing on the other side. So now we have a parabola going through the same vertex, but the curve here, the sides, go up much faster. So what happened to the parabola for g of x? It was stretched. And it was stretched by a factor of 2. So that means it was doubled. For h of x, this time we have a, instead of being a 1, we have it being a 1/2. This tells us that we are going to have a compression because the values are going to be halved. So instead of a 4, we should end up with a 2. So looking at the same x values so that we can determine, or at least look at them side by side. So we get a 2 here. This yields a 1/2, a 0. Again, they share a common vertex. 1 yields a 1/2, and 2 yields a 2. So you can see that we took these values and they were halved each time. So to plot these, if I go over negative 2, I'm going to go up to positive 2. If I go over negative 1, I'm going to go up 1/2, and that's going to be a little tough to get up in there. 1 gives me to 1/2, and 2 gives me to 2. If we want, we can go ahead and extend this graph or this table, and we can do a negative 3. Well, no, let's do negative 4. So let's look at negative 4. Negative 4 is going to give us a positive 8. So if we go out here with negative 4, we can go up to positive 8. And that means that a positive 4 will also give us, I can look at the table of values and see that a positive 4 also gives us an 8. Just so that you can see a little bit better how this is flattening out. So we took this line here, the parent function, and it's brought out. It's been opened up. So in g of x, we took this and we stretched it up, but in h of x, we compressed it. So this was compressed by a factor of 1/2. Let me take care of this one right here. It doesn't really look like an S since I messed up there. Okay, compressed by a factor of 1/2. Okay, so that is a change to C, and this is a change to A. So now let's look at a change to the sign. So we'll go over here, and our parent function, again, we will use negative 2, negative 1, 0, 1, and positive 2. That is how we got these values here. Now for g of x being negative x squared, we're still going to use negative 2, negative 1, 0, 1, and 2. So you can go ahead and write those in. So we have -2, and I think I'm going to use red on this one just because I think it'll be a better contrast to the black. So -2, -1, 0, 1, and 2. So we go to the calculator to y equals, and we say -x². And we look at the table of values. So here we get -2 becomes -4. -1 is -1, 0 remains 0, 1 becomes -1, and 2 becomes -4. So when we compare these x values, they are indeed opposites. So as we plot these points, -2 gives us -4, -1 gives us -1. They share that vertex of 0, 0. 1 gives us -1, and 2 gives us -4. So what we have here is a parabola that opens down. This has a maximum, whereas the parent function had a minimum. So anytime you see this situation here where there's a negative sign in front, then you know you're going to have a maximum value and everything else needs to be below that. So what happened to the parabola? It was reflected. So you could say that this is like a body of water, like a lake, and you have this tree up here and now it's reflected down here. So that is the third example, and now we will do a couple of examples where we change not only one but more than one of the possibilities can occur. So let me restate that. So we could have a reflection, stretch, and a translation. We could have a reflection, a compression, a translation, any combination of those three things. Again, the parent function, we're going to use -2, -1, 0, 1, and 2. So we can get those filled in here. For g of x, again, we're going to use the same numbers so that we can get a good representation. And we can put this into the calculator. We have -x² plus 1. So just looking at what's happening here, A went from a +1 to a -1, so that's going to be a reflection. C went from 0 to a +1, so this is going to be a translation up. So looking at the table of values, we end up with -3, 0, 1, 0, -3. So they will not share a common vertex. So let's plot these points. -2 gives us a -3. 1, 2, 3. These are a little small for my eyes. And then -1 gives us a 0. 0 gives us a +1. As you can see, they no longer share that vertex. And then 1 gives us a 0, and 2 gives us -3. So these points have been plotted. Now we can connect the points into a curve, and we can see that indeed it did flip over, so that's a reflection, and then this vertex was moved up 1 unit. So what happened to g of x? It was reflected and translated up 1 unit. Okay, next and final example is for h of x to be 1/2x² plus 3. Again, we will use the -2 to 2 for our domain. Then we will go to y equals and type this in. So alpha y equals to get our fraction. So there's 1/2 x squared. Whoops, that's the root of 1/2 x squared plus 3. And then look at the graph, and here are our values. Now notice that we have 7 halves. So I will do like I did over on this example and use some different numbers here in just a minute. I want to go ahead and put these in. I have 3, 7 halves, and 5. And we can see that the even numbers yield whole numbers. This is going to be off the graph, but I can still get an idea of where it's going to be. So if I come down here to positive 4, it too will be off the graph. So let's see what we can do to plot these points. So at negative 2, I'm going to get a positive 5. So here's 4, 5, right there. At 0, I get a positive 3. And at 2, I get a positive 5. And then let's see if we can figure out this 7 halves. 7 halves is the same as 7 halves is the same as 3 1/2. So if we go to negative 1, we're going to go up 1, 2, 3 1/2. Same thing over here with positive 1. You're going to go up 1, 2, 3 1/2. Those get a little difficult. And we know that out here at 4, we wanted to go a little bit above, and at negative 4, a little bit above. Those came out to be 11 when we looked at the table of values here. So, trying to shoot for that, we can see that this one got wider. So this one was a compression. There was no reflection. It could have been, but there was no reflection, but this one was compressed, but it was also, this vertex was moved up 3 units. So it was compressed and translated up 3 units. So to recap, when b equals 0, we were looking at the transformations of C, A, and if A was a sign change or not, remember that this was a reflection. If it changed from positive to negative, A, a stretch, and that meant that A was greater than 1, and it was a compression when it was smaller than 1, and then C was our translation. It would be up if it's positive, and let me put that more in an inequality form. So if C is greater than 0, then it goes up, and down if C is less than 0. So here we have our translation. Here we have either a stretch or a compression, and here we have a reflection, and this is when it is a sign change. Okay, thank you for your attention.